Hello everyone, welcome back to another lecture on the topic of polynomials. This time we want to discuss something totally new, and that is polynomial inequalities. When we talk about polynomial, well, a linear function counts as a polynomial function, even quadratic counts as a polynomial function, and then cubic, quartic, quintic, and so on and so forth. So we will first focus only on linear and quadratic inequalities. What you see here, it says 3x minus 17 is less than or equal to 2 times x plus 5 minus 19. So what you see here is what we call it a linear inequality. Why inequality? Because we don't have the equality sign and it's not an equation. Instead, it's an inequality. Left side is less than or equal to right side. And we want to find values of x, not necessarily one or two values, not necessarily like 3 or 4 values. It could be like infinite number of x values. We want to find these x values that satisfy this inequality, okay? So why do we call this linear inequality? Because all the expressions are linear. You will never ever see an x with an exponent of 2 or 3 or 4 or something like that, okay? So that's why we call this linear inequality. This one is a quadratic inequality because the exponent of x is 2. So that's a different story. And then if the exponent is x cubed, if the exponent is 3, 4, 5, we have x cubed term, x to the 4 term, and so on and so forth. Those are like more complicated polynomial inequalities that we will discuss later on. So first I want to solve this inequality. So again, just like equations, I'm going to bring all the letters on one side and all the numbers on the other side. So we are isolating the variable on one side of the inequality. And we get 3x minus 17, that's 2x plus 10 minus 19. So this is 2x minus 9 if you collect like terms. And if I bring all the x's to one side of the equation, I get 3x minus 2x. Same rule applies. 2x on the right side becomes negative 2x on the left side. And then 17 minus 9, which is 8, I believe, right? Okay, so 8 and 3x minus 2x is, of course, x. So we simplified this linear inequality and we ended up with x is less than or equal to 8, okay? So saying that 3x minus 17 is less than or equal to 2 times x plus 5 minus 19 is the same as saying that x is less than or equal to 8, basically. So what is the solution set? Well, any x value, any real number that is less than or equal to 8 would satisfy this inequality. For example, you can select 7, 7.5, you can select 6, you can select 0. If you select 0, we end up with negative 17 on the left-hand side, and this would be 0, so 10 minus 19 is negative 9. So we get negative 17 less than or equal to negative 9, which is actually a true statement. So you see that x equals 0 satisfies the inequality. In fact, not only 0, any other x value less than or equal to 8 would satisfy this inequality. And that's how we got the solution. You can select x to be negative 1, negative 4, negative 5. So you see that millions of solutions are there. So it's not like the equations when we used to say, okay, x equals 5 is the solution to this equation. It's not like that. We have something, we call it solution set, not like a fixed number as the final answer. So when it's solution set, we have to write the solution set inside the brace brackets. And we're saying x belongs to the set of real numbers, okay, such that x is less than or equal to 8. So that becomes the solution set for this inequality. So get used to it. For inequalities, we don't have like one final answer. Very, very exceptional cases, very rare cases. But 99.9% of cases, when you have an inequality, you will end up with a solution set, okay? Now, this solution set is clear. We understand that. It says any real number less than 8 is okay. It satisfies the inequality. But we want to visualize this solution set. Therefore, we draw a graph of the solution set. When I say graph, I don't mean like some sort of graph of like a parabola or something like that. just graphing the solution set. So if I have a number line, okay, which represents the set of real numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on the right, 2, 3, 4, negative 4, 1, 2, 3, 4, negative 8, and so on and so forth. This is just the number line. Now we are saying that x is less than or equal to 8. So 8 is right there, okay? Less than means to the left, not to the right. So any x value that is less than or equal to 8 takes into account, and that's part of the solution set. So this graph here, okay, which has a solid dot at 8, and it means that x can be equal to 8. This is called the graph of the solution set, and it's a way that you can visualize the solution of the inequality, basically. If we end up with x less than 8, only, strictly less than 8, then here we have to draw an empty circle or a hole, excluding 8 itself. The story of linear inequality, I gave you the example. The rest is up to you to sit down and just keep practicing to become better and better and better at it. Quadratic inequalities are a little bit harder. For these ones, what we're going to do, we're going to try to factor them. If you factor a quadratic trinomial, you end up with two linear expressions. That will be easier to take care of solution of these inequalities. So here, I'm going to factor first, okay? And we get 3, we get 2, plus and minus, okay? Two numbers add up to -1. The product is -6, are 2 and -3. So what did we end up with? We end up with two binomials, the product of two binomials being less than 0. So these binomials represent numbers end of the day for different values of x. Now, when do you think two numbers or product of two numbers is negative? Obviously, either one is positive, one is negative. Because if both are positive, how come the product is negative? That's impossible. And if both are negative, again, the product is going to be positive. That's impossible again. So there must be either this case where one is positive, the other is negative, or one is negative, the other is positive. So they must have opposite signs, basically. But it's, again, difficult. It's difficult to guess, or what x value would make x plus 2 negative, what x value would make x minus 3 positive, and then what if it's the other case. It's very difficult to just sit down and guess. Therefore, we use a systematic method that I'm going to explain. So we're going to construct a chart, okay? So in the top row, we have x, which represents our independent variable, and it's a real number end of the day. And in the left side column, we are going to list all the factors that we have in our inequality. So x plus 2 is one factor, x minus 3 is the other, and if I call this p for the product, so then the product is what we want to find its sign. And x may vary from negative infinity all the way to positive infinity. That represents sort of number line. And we have roots of these factors. One is -2 and one is 3, okay? How did I know it's -2? Well, you can set x plus 2 equal to 0 and solve for the root. X will be -2. X minus 3, what is the root of x minus 3? It's positive 3. Why? Because 3 minus 3 is 0. Or you can set x minus 3 equal to 0, solve for x. So end of the day, these are the roots of those factors. And I'm going to subdivide my chart into sub-intervals, okay? So now I have this table here, and we are saying that x plus 2 equals 0 if x is -2. That is very clear. And x minus 3 is 0 whenever x is equal to 3. So if x equals 3, x minus 3 equals 0, period. About the product, I can say the same thing, because if any of these two factors is 0, the whole product will become 0, obviously. So I'm going to say at -2, the product is 0, and at x equals 3, the product is also 0. So I did take care of zeros first. Now I'm going to say x plus 2 will have a positive value if x is larger than -2. Think about it. You pick like -1, you pick 0, 1.5, you pick 10 million, plug in for x, you end up with a positive number, right? So to the right, we have positive, but to the left, we have negative because x plus 2 has a negative value if x is less than -2 on the left-hand side. So you pick -3, -4, -5, you plug in here, you end up with a negative answer, obviously. So that's why we're saying x plus 2 has a negative sign if x is less than -2. And x minus 3 is positive if x is greater than 3, and it's negative if it is less than 3, obviously. And the product of negative and negative is going to be positive. Positive times negative is negative. Positive times positive is positive. So we could, by this chart method, we could successfully determine the plus minus sign of the product that we have. So now I exactly know where the product of these two binomials is positive, over what interval it's negative, where it's positive. I clearly know that. Now the thing is that we wanted our quadratic trinomial, the product, be negative, right? Strictly negative. That means in the middle. So that means I have to basically not count the positive parts. So I'm going to erase these parts or shade these parts. These are not part of the solution, and only the middle part is what I need to take into account, because only when x is between 3 and -2, the product is negative, and we wanted actually the trinomial to be negative. Less than 0 means negative. So I'm going to say the solution set is all real numbers such that x is trapped in between -2 and +3. So if x is between -2 and 3 exclusive, not inclusive, then we would end up with a negative sign for this quadratic trinomial, and our inequality will definitely be satisfied. So that's the solution set. The graph of the solution set this time would be 3 and -2, but I'm drawing holes or empty circles, not solid dots, because the equality case is not taken into account. And any number in between these two, of course, it's okay. So I'm drawing just the graph of the solution set so that you visualize the solution set. Any x number you select, 1, 1.5, 2, or -0.5, -1.2, whatever you select in between, it's going to satisfy that inequality, which means that this is actually the solution set. Now, this is the algebraic way of doing it, but there is an interesting graphical method of solving these inequalities, and that's the following. You see this x squared minus x minus 6, it's a quadratic trinomial, okay? If I set y equal to x squared minus x minus 6, that would be actually a quadratic function whose graph will be a parabola. I took the liberty of graphing this parabola. We have learned like 2-3 years ago how to graph parabolas. So I did draw the graph of the parabola. I have the vertex, I have the axis of symmetry, x equals 1/2. You know, I'm not explaining how to graph parabolas. Everybody knows that. You can even use technology to graph it if you want. So, but the thing is that you may notice that this parabola has two colors. The green part is the part above the x-axis in the positive region, where y is greater than 0. All the points on the parabola, on the green part, which are above the x-axis, have a positive y coordinate. But on the other hand, the bottom part, which is negative, that's the region where y is less than 0, that is negative. Any point on the parabola will have a negative y coordinate if it is below the x-axis in the negative region. That is in the red part of the parabola at the bottom, okay? So when we talk about the parabola, we're talking about x squared minus x minus 6. In other words, we talk about y. And we want this y, so this is actually y here, right? So y, we want y to be less than 0. That's the question, okay? That's the given question. You want to solve an inequality where y is less than 0. In other words, y is negative. So you look at the graph and find out where or over what interval y is negative. So clearly from one x-intercept, which is -2, up to the other x-intercept, which is +3, in between, we see that y is negative, okay? But then if x is more than 3, then you have a point on the green part of the parabola where y is positive. So again, graphically speaking, you can easily look at the inequality and say, okay, because y is less than 0, therefore the answer must be the lower part of this parabola, that is, x has to be between -2 up to +3, the two x-intercepts of the parabola. And you get exactly the same answer as you see. Now, if this direction was the other way, if it was saying trinomial is greater than 0, Then in the chart method, we would take into account the positive parts. And in the graphing method, we would take the green part and the green part over there. We would say x must be less than -2, or it has to be greater than 3. That's what we would say, okay, if y was greater than 0. Okay, I hope you understood how to solve linear and quadratic inequalities. I hope you understood the chart method, the graphing method, and how we write the solution set and how we graph the solution set. Perhaps in the next lecture, I'll give you a more complicated example with a polynomial inequality. Keep practicing. Thank you.